All right. Well, happy week 10, and it's June. You just have like a couple of weeks left. So, I'm gonna download. I think I have. I just want to make sure the script PCA for image example. Oh, Imager. You always forget. My home computer and the computer I bring to work are different. Okay. I hope this works. All right. So I introduced PCA on Friday, and I introduced it as this kind of way for dimension reduction, and dealing with reduced dimensions is just easier for our brains to kind of think about. And you can kind of really lean into PCA, and there's all kinds of stuff you can do with it. You can do like, once you get your principal components and you project your data, then you can do like linear regression on that and things like that. And so you'll have uncorrelated predictors. It's just, interpretation itself becomes a little bit trickier because now each of your variables is a linear combination of the other variables, right? So anyway, but I thought just kind of like a neat but completely unnecessary, and maybe not even useful thing that we can do is I wanted to show like you can use dimension reduction almost as a form of like image compression, basically like compressing your data. And one thing that's kind of neat about seeing it as a form of like data compression is you can almost using an image, you can visualize how much information is lost. Okay, so let me, I'm going to load up this package. Whoops, I just installed it. Okay, so that one's installed. All right, we're going to load up this library. And then session set working directory to source file location. Okay, let me load this image up. Okay. So I'm going to load up this image. This is from, are you guys familiar with Ansel Adams? This like nature photographer. He has like famous, his famous photos are from like Yosemite. I don't know, let's see. I don't want a picture of himself, but like, like black and white photos, like these beautiful pictures of like Yosemite Valley, and this would be Half Dome and things like that. And anyway, like I think that I saw like a video clip, like a documentary video clip of him doing like his film exposures and stuff. And so this is all before the days of Photoshop, and he would like I don't know, use like things to cast shadows during the film exposure process to kind of enhance the contrast and the lighting and things like that. So anyway, so I'm going to load up an image of, I guess, Snake River. Okay, so this is one of his images, and it looks way better on my screen than it does on this classroom projector. So, but all right. So anyway, there's a package called Imager, and basically it will read in the image, okay, and it kind of treats it as a matrix, okay. And so basically you get this image is 899 pixels by 720 pixels, so you get this very large kind of matrix, and basically values range from 0 to 1, and I think 0 means the pixel is black and 1 is the pixel is white, and like everything in between is either a dark shade or a light shade of gray or something in between. I think maybe I have it backwards, and so anyway, we can call plot on this image, and then it appears right here. Okay, and so we can kind of, this is an image, but you can also think of it as like a data frame where you have 720 rows, okay, and 899 columns, and you can think about these columns being like different variables. And if you think about two columns, that is two just vertical line of pixels that are next to each other, they're going to exhibit high correlation, right? Like if you think about this stripe of pixels going up and down, and then the stripe of pixels right next to it, they're probably going to exhibit a lot of correlation, especially like in the parts of the sky. And it's like really only where you have like, I guess, structure and stuff and things like trees and things, you're going to get a little bit of variation. But overall, a lot of these columns are going to be highly correlated. And so this kind of puts us in a position where, oh yeah, maybe we can do dimension reduction, where we can take our correlated data and create some kind of alternate projection of uncorrelated data. Okay, so I'm going to go through the process of, I guess, principal components analysis for this thing, and we're going to just treat it like it's a big matrix or a big data frame. 720 rows. That's how many pixels rows of pixels I have. 899 pixels wide, so 899 columns. Okay, so the first thing is I have to center my each of my columns. So we want all of the centers to be at 0. Okay, so I'm going to take the columns and I'm going to subtract the column means from basically all of the values. Okay, and so that's what I've done. And then I'm going to just check to see, are all of the column means now equivalent to 0, and that comes back as true. Okay, and I can plot this as well. Except we want to now do the centered. Okay, and I don't know if you can see what has happened, but basically the image looks almost exactly the same, except it's brought in like these kind of these streaks, okay, these vertical streaks. And basically what has happened is that this part of the image has these, like, I guess if you take that column of pixels, its average pixel is like bright, okay? So bright would be like a value closer to 1, right? And so it's going to take that average and then subtract off everything. So that's going to have the effect of darkening basically that column of pixels. And then maybe over on this side, the average pixel over here, because there's kind of a lot of kind of shadowy area over here, even though it's like brighter over here, I guess the overall average here is kind of on the darker side. And so its average is going to be, I guess, closer to 0. And if you subtract that off, okay, and you kind of recenter everything, it's going to have the effect of kind of like brightening that column of pixels. And so what you see is like certain parts of the image are darkened, certain parts of the image are like brightened, but everything is applied vertically. So you just get these kind of vertical streaks of things that are getting darkened and brightened and stuff like that. It's a little bit harder to see in the on the projector, but I don't know if you guys can kind of see the effect of these vertical brightening and darkenings there. Okay, so anyway, that's what I have. I'm going to go ahead and calculate a covariance matrix. So this is kind of computationally expensive, but I'll go ahead and I'll do it. Whoops. Okay, so the covariance matrix, if I ask for what are the dimensions of the covariance matrix, it's going to be 899 by 899. So we can, let me just back up and say this idea of using principal components analysis as a way of data compression is actually a valid concept for like trying to compress files or image files or things like that. It's a valid thing. However, it is not used because it is computationally expensive. So anyway, we use probably as far as like image compression forms where you're okay with losing some data would be the most popular, would be like the JPEG. And I don't know if you guys are familiar with JPEGs, but like if you over crank the image compression of a JPEG, it gets like really blotchy and hard to see and stuff like that. And some similar stuff happens here is because these are I guess destructive image compression form things where it's like you lose information when you compress it. Okay, but anyway, I've created a covariance matrix. This covariance matrix is 899 by 899. So we're actually increasing the amount of data that needs to be stored, because the original thing is a matrix that's 720 rows by 899 columns. So, what is 720 by 899? 720 times 899. Not D720. 720 times 899. 647,000 values, and 899 times 899 is 808,000 values. So this actually has more values to store. And we will calculate the eigenvectors and eigenvalues of it. Okay, so I have this kind of big matrix. The original matrix is 899 by 899, the covariance matrix, and then when you calculate the eigenvectors, you get 899 eigenvectors, and so your matrix of eigenvectors is also 899 by 899. Okay, but what we can do is I can say, like, let me just keep the first 50 eigenvectors. Okay, so I'm going to take this matrix 899 by 899, and I'm going to just keep the first 50 eigenvectors. Okay, and these will be kind of my so I'm going to call this PC50, my first 50 principal components directions, and then so I'm going to take my original data, 720 rows, 899 columns. I'm going to multiply it by this 899 by 50 matrix. Okay, and so my projected data is now 720 rows, 50 columns. Okay, and if I try to plot this, my projected, Adams projected, it is not going to make any kind of visual sense at all, right? So this is, we have projected the original 899 columns down into 50 columns, and this is the thing, and there's not, and it's actually not really interesting. There's a whole bunch of gray, and actually most of the interesting stuff is all the way at the left, where there's actually some contrast going on, but it's like impossible to tell what's going on. Okay, and the idea here is this, it just doesn't make sense, and I mean, it doesn't interpret for us, because what we've done is we've found a rotation of the data So this is not a rotation of the image, but it's like the columns, 899 columns, and we've found some lower dimensional projection of this, okay? And what we have to do now is we have to kind of take this reduced data and try to recreate the original data, okay? So this is, so if you have two-dimensional data, okay, and you think about it like this, okay, a pure rotation will kind of take all of this and project it down, you know, to something like this, okay? And then we reduce the number of dimensions by just kind of throwing away the second thing, and you just second dimension, and we're down to just one dimension, okay? And right now we're just looking at this one-dimensional projection here, but it doesn't quite make sense because we're expecting our data to have a two-dimensional form. We're expecting our data to be two-dimensional. So what we want to do is we want to kind of undo the rotation even though we've lost information. Okay, so we've gone from here. And so when you undo the rotation on one-dimensional data, it's going to still retain its one-dimensional structure, okay, but it will now be in a two-dimensional form, okay? And so we're basically going from here to here, right? So there's more information here. We lose that information, but this is now in a form that we can kind of recognize, right? And this is basically what we're going to do, except you have to go from 899 dimensions. This is the rotation, 899 dimensions. We're reducing it down to 50 dimensions, and this isn't a rotation that doesn't make sense, but we're going to undo the rotation and project it back to 899 dimensions, okay? But what we would do is, as far as image compression goes, you would go through the process. This is the package that you would package up, okay? You would package up this thing. This would have like less content, and then once you send this over, you would give instructions to kind of like unpackage or unzip to recreate 899 dimensions. If that kind of makes sense. So we would kind of transport this thing, 720 by 50 values, so you know, a lot fewer values to have to kind of transport, and then we would say, all right, reconstruct the original image by kind of undoing that rotation, okay? And so the reconstructed image is back to 720 by 899 pixels, okay? And you'd have to kind of recenter it. So let me delete this, and let me delete that. So this is the original data, and this is kind of my reconstructed image, okay? So I don't know if you guys can see. So here is the original image, and this is after kind of compressing the data down to 50 principal components, doing the rotation, and then undoing that rotation. So we compressed it down to 50 principal components, and we said, now reconstruct the image using just these 50 principal components. And so you get a lot of the original, so compared to the original image, this is certainly not as high, it's blurrier, and you lose some of the detail, especially in the forest and things like that. And the clouds are kind of streaky and whatnot. But you retain a lot of the informational structure, okay? And if you think about like how much kind of compression was applied, we basically went from 899 pixels down to, or 899 columns down to 50 columns. And so, you know, it's around 5 to 6% of the number of columns that we had to retain to kind of keep this kind of structure here. And we could see like, okay, well, what would happen if I didn't keep the first 50 principal components, but what if I only kept like 5 principal components, okay? What would happen? Okay, this is what you would get, okay? So keeping only 5 out of 899 principal components, you get this. Now, if this is the original image, and here is the image after 5 principal components, you see, okay, we've lost a lot of information. But at the same time, it's not terrible considering that we went from 899 down to 5, right? It's kind of like if I look at something and I take my glasses off, I'd be like, oh yeah, that's that's the thing, right? It's like kind of just like looking at something through some blurry idea, something really blurry. And so here, I kind of ran a loop here where I'm going to just try out different numbers of principal components. So we're going to go 1 through 10, then 12, 14, 16, 18, 20, 25, 120, 150, 180, up to, 300, 400, 500 out of the 899 things, okay? And for each of these things, I'm going to go through the process of keeping only a subset of those principal components and then projecting it down and then reconstructing the image after projecting it down. Okay, so I'm going to go ahead and just run that, and I'm going to save all of these. All right, I think okay, well, so these are small. So this is, if you keep only one principal component, this is the resulting, and you say, all right, reconstruct the image after that. This is the resulting image, okay? It looks terrible. Compared, the original, where's my original image? We want Snake River. All right, so here's the original image, and this is what we have. So basically all it does is it kind of just says, all right, this area is dark, this area is bright, and this area over here is just gray. Okay. With keeping the second principal component, it adds stuff. Okay. Here it is with 3, and then 4, 5. Okay, and now we're starting to see like, oh, there's a river or something. Okay, maybe if you don't know what the original image is, you still have no idea what this possibly could be. But here we have the original kind of the sky, the mountains, and then the river. And we're starting to see things. Okay, 6, 7 principal components retained, 8, 9, 10. And then I start going up by 2s, 12, 14, 16, 18, 20. And I don't know at what point you say, all right, well, that's good enough. Okay, 25, 30, 35, 40, And at this point, adding 10 additional principal components, going from 40 to 50, you don't see a whole bunch of change. Here it is 70, 90, 120, 150, 180, 210, and that's with 500 principal components. So at 500 principal components to 400 principal components, what's the difference? I don't know. Basically, the idea is if we went from 899 pixels down to, say, I guess 899 wide, we can find kind of like a projection, almost kind of like you can pick like 210 columns and just say like these would be like almost like representative of like their neighbors and stuff, and then you get something kind of similar looking here. On my screen, there is a little bit of a subtle difference going from say 210 up to 500. I don't know if you can see the difference, but as I reduce the number of principal components, one thing that is kind of going on is there's a reduction in the contrast of the image, okay? So contrast is kind of like how different, high contrast means the bright and white parts of the image are like really white, and then the dark and black parts of the image are really dark or black, okay? So high contrast, so like a TV might sell this high contrast ratio to kind of indicate that like in a movie scene or something, if some area is supposed to be really bright, it's going to be really bright, and if some parts are supposed to be black, it's really dark, right? Versus like, one thing that we really lose when you have a projection in the classroom is that the contrast ratio between, so like, what color is this supposed to be? It's supposed to be black, right? Okay, and this is supposed to be white. However, if I turn off the projector, okay, or if I just cast a shadow, like any other day, and I say, what color is this? You'd say it's white, okay? But this is the exact same color as this, right? So, so that like, this is what we lose. In a classroom like this thing, we would all say this screen is white, but then it's also supposed to represent black on the in a projector, and I guess like the light makes this part even brighter. But like basically the contrast ratio between this and this is like terrible, and so it's hard to kind of illustrate some of these concepts. But like on a TV, like you don't want to watch a movie on this, right? It's like not. At least like turn the lights off in the classroom, right? And then turning the lights off in the classroom has the effect of making this part, this white projector screen, like become dark. It's not reflecting off as much light. But anyway, retaining additional principal components is basically going to capture more of the variation in the original image. And if you think about what is variation in an image, especially a black and white image, variation is basically the difference between bright pixels and dark pixels. And so when you keep more principal components, you're basically able to reproduce more of that variation where you have bright pixels and dark pixels. So that, and that would correspond, at least from an image sake, differences in contrast. So, so like going from like say 30 pixels to 200 pixels, or 30 principal components. As you increase that, you get a little bit more structure, and then 250 to 500 principal components, you get more of this. I don't know. Did any one of you like try downloading the script and running it? And is it running and producing a bunch of the things? Okay, you might be able to see a little bit better on your screen then some of the differences between these things. Okay. Anyway, this was all just for a black and white image. Technically, Imager, this package, can also do color images. But basically you would have 3 color channels then. So images, basically all of the, it's interesting how our eyes work, but like you have a red light, a green light, and a blue light, and somehow like that's enough to capture all of the colors that we see. And so shades of gray are basically red, green, and blue are at the same intensity. So you'd be like red, green, blue, all level 100. It's, one color of gray, red, green, blue, all level 200 is a different color of gray. But if you have like red 200 and green 0 and blue 0, that's going to be a shade of red. And then, red and green mixed together gives you like shades of yellow, and green and blue mixed together gives you like cyan or something. Red and blue is like magenta. And so anyway, you have, you could load in a color image, but then you have basically 3 color channels that you have to account for and whatnot. But that's that. Again, we don't actually use this as far as image compression goes for the internet, because doing your covariance matrix and then undoing it is computationally expensive. I mean, today it doesn't really matter, but I guess back in the day, early days of the internet, it was not a preferable method. So we use like JPEGs and things. But yeah, that's I guess, I don't know if it's fun, but I thought just kind of like a neat little illustration of like what's happening when we talk about reducing the dimensionality of our data. Is we're basically trying to retain as much of the original information with, I guess, as few principal components. And then, once you have that reduced information, you can try to reconstruct the original data, but there's certainly a loss of information, okay? But this, it's easier to think about 5 things versus 899, okay? And again, if you think about like, okay, complicated things that you have to make comparisons for. So for example, trying to compare, one candidate with another candidate, right? People being complicated things, if you could kind of just score them on like 5 different aspects, right? You just say like, okay, we want to know like, what is this person's academic ability? What is this person's like leadership skills or something, right? And you just kind of come up with these, these are like the 5 important things that we're looking for, and we give them a rating, 1 through 10 on each of these things. And it's a little bit easier to kind of think about your candidates if you just have like five aspects to think about rather than like 500. But again, when you go down to 5, you lose a lot of kind of nuance and detail and stuff like that. Okay, so that's that for principal components analysis. I don't know. I hope it's okay. This week is going to be kind of like optional lectures and stuff. So Wednesday I plan on going over like decision trees and random forest and going over stuff like that, because it's kind of like a machine learning topic. But it will be stuff that I'm not going to put on the final exam. I guess on Wednesday I'll also talk about what you can expect to see on the final exam, which is, I guess, coming up. So, all right, we'll end, I guess, a few minutes early today. Thanks for coming to class, and I hope you guys have a good week 10, and we'll see ya Wednesday then.